Assalamu alaikum. Today I want to talk about Chapter 8, Basic Concepts of Chemical Bonding. Now, whenever two atoms or ions are strongly held together, we say there is a chemical bond between them. There are three general types of chemical bonds: ionic, covalent, and metallic. Now, in this chapter and the next, we examine the relationship between the electronic structure of atoms and the ionic and covalent chemical bonds they form. So as I said, there are three basic types of chemical bonds. Ionic, which refers to electrostatic attraction between ions. Covalent refers to sharing of electrons between atoms. And metallic, metal atoms bonded to several other atoms. Here you can see an example for ionic bond, for example, in magnesium oxide, electrostatic attraction between magnesium and oxygen. Here metallic, for example, in sulfur, bromine, sucrose. And here metallic, you can see a metallic bond in gold, copper, and magnesium, which are formed by electrons that are relatively free to move through the metal. Now, we come to section 1, Lewis symbols and the octet rule. Now, Lewis structure for an element consists of the element's chemical symbol plus a dot for each valence electrons. Example, sulfur. As you studied in the chapter 2 in the periodic table, sulfur is in a group 6A, so it has 6 valence electrons. Now each valence electron is represented by a dot, so the dots are placed on the 4 sides, as you can see, of the symbol, since all of them are equivalent. You must distribute them in this way, so they are on all 4 sides of the atom. Question here: are all these Lewis structure for Cl correct? You look at them. Chlorine is in the group 7A, so it contains 7 valence electrons. So here 2, 2, 2, and 1, this is correct, and here 2, 2, 2, 1, this is correct, but this one only we have 5, so this is incorrect. Now, the octet rule. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. An octet of electrons consists of full S and P subshell in an atom. So in Lewis symbol, an octet is shown as 4 pairs of valence electrons arranged around the element symbol, as مثلا in the Lewis symbol for neon and argon. طبعا there are exceptions to the octet rule, but it provides a useful framework for introducing many important concepts of bonding. Now we come to section 2, entitled Ionic Bonding. Now, ionic substances generally result from the interaction of metals on the left side of the periodic table with non-metals on the right side, excluding the noble gases group 8A. Now, for example, when sodium metal Na is brought into contact with the chlorine gas Cl2, a violent reaction results. Now, the product of this very exothermic reaction is sodium chloride, NaCl. According to this equation, you see, delta H0 formation equal minus 410.9 kilojoule. Now, sodium chloride is composed of sodium ions and Cl minus ions arranged in a 3-dimensional array. Energetics of ionic bonding. Now, removing an electron from sodium atom to form sodium ion, for instance, requires the input of 495 kilojoule per mole. When a nonmetal gains an electron, the process is generally exothermic, as seen from the negative electron affinities of the elements. So, as we saw in the last chapter, it takes 495 kilojoule per mole to remove electrons from sodium. This is the amount. And adding an electron to Cl, for example, releases 349 kilojoule per mole. Now, from the magnitudes of these energies, we can see that the transfer of an electron from a sodium atom to Cl atom would not be exothermic. The overall process would be an endothermic process that requires the input of this amount, 146 kilojoule per mole. So again, as you can see here, we get 349 kilojoule per mole back by giving electrons to chlorine. Now, ionic substances possess several characteristic properties. They are usually brittle substances with high melting points. They are usually crystalline. Also, ionic crystals often can be cleaved, that is, they break apart along smooth, flat surfaces. Okay, now, again, but these numbers don't explain why the reaction of sodium metal and chlorine gas to form a sodium chloride is so exothermic. So if we look here, the reaction between Cl2 gas, as you can see, and sodium metal to form sodium chloride crystals. So what we can say, no, there must be a third piece to the puzzle. What is yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and chloride ion. So again, sodium atom loses an electron to become Na plus ion, and Cl atom gains an electron to form Cl minus ion. And since they are oppositely charged, there is electrostatic attraction between them in the newly formed compound called NaCl. Now, lattice energy. The third piece of the puzzle is the lattice energy. The energy required to separate a mole of a solid ionic compound into its gaseous ions. Now, the magnitude of the lattice energy of an ionic solid depends on the charges of the ions, their sizes, and their arrangement in the solid. Now, the energy associated with the electrostatic interaction is governed by Coulomb's law. This one. Two interacting charged particles. Now, in this equation, Q1 and Q2 are the charges on the particles, D is the distance between their centers, and K is a constant. It has a certain value, 8.99 times 10 to the 9 joule meter per Coulomb square. Now, this equation indicates that the attractive interaction between two oppositely charged ions increases as the magnitudes of their charges increases, as you can see here, and as the distance between their centers decreases. Thus, for a given arrangement of ions, lattice energy increases as the charges on the ions increase and as their radii decrease. Now, the magnitude of lattice energies depend predominantly on the ionic charges because ionic radii vary over only a limited range. Now, lattice energy then increases with the charge of the ions. and also increases with decreasing size of ions. Now, look at this table, which shows us the lattice energies for some ionic compounds. You see how lattice energy increases with increasing the charge and increases also with decreasing the size. Notice here Mg plus 2 with oxygen minus 2. Here we increase the charge, so it is greater than, for example, Mg here plus 2 and Cl minus 1. So you see the difference. Also here SrCl2, Sr plus 2 and Cl minus 1, this number, whereas here SrO, Sr plus 2 and oxygen minus 2, so the lattice energy increases, as you can see this. Now let's look at this sample exercise talking about magnitudes of lattice energy. Now, without consulting the table, arrange the following ionic compounds in order of increasing lattice energy: NaF, CSI, and CaO. Now, from the formulas for 3 ionic compounds, we must determine their relative lattice energy. Now, we need to determine the charges and relative sizes of the ions in the compounds. We can then use equation quantitatively to determine the relative energies, knowing that the larger the ionic charges, the greater the energy, and the farther apart the ions are, the lower the energy. Now, NaF consists of sodium ion and fluoride ion, CSI of Cs plus and Ci minus ions, COO, Ca plus 2 and O minus 2 ions. Now, because the product of the charges Q1 times Q2 appears in the numerator of the equation, the lattice energy will increase dramatically when the charges of the ions increase. Thus, we expect a lattice energy of COO, which has a plus 2 and minus 2 ions, to be the greatest of 3. So, CaO is greater than both of them. Now, the ionic charges in NaF and CSI are the same, plus 1 minus 1 plus 1 minus 1. So now we must compare the size. As a result, the difference in their lattice energy will depend on the difference in the distance between the centers of the ions in their lattice. Because ionic size increases as we go down group in the periodic table, we know that Cs plus is larger than Na plus and I minus is larger than F minus. Therefore, the distance between the sodium atom and sodium ion and F minus ion in NF will be less than the distance between Cs plus and I minus ions in CSI. As a result, the lattice energy of NF should be greater than that of CSI. So, in order of decreasing energy lattice, we have CSI less than NaF and NaF is less than CO. So this is an all arrangement in order of increasing lattice energy. Now, this phenomena also helps explain the octet rule. Metals, for instance, tend to stop losing electrons once they attain a noble gas configuration, because energy would be expended that cannot be overcome by lattice energy. Now, electron configurations of ions of the S and P block elements. The energetics of ionic bond formation helps explain why many ions tend to have noble gas electron configurations. For example, sodium readily loses one electron to form an A+, which has the same electron configuration as neon. So, an A atom has this electron configuration, neon 3s1. After it loses this outermost electron, it becomes sodium ion, and it has the same electron configuration as neon, which has an octet of 8 electrons in the last shell. Now, similarly, adding electrons to nonmetal is either exothermic or only slightly endothermic. Now, if the electrons are added to the valence shell, thus a chlorine atom easily adds an electron to form Cl-, which has the same electron configuration as argon. And the atomic number of Cl is 17. So the electron configuration neon 10. Here we have 3s2 and 3p5. 5 plus 2, 7, plus 10, 17. Now by gaining an electron, now the gained electron is added to p orbital. So we have here 6 plus 2, 8. So it has now 8 in the third shell. And this is, if you add all the electrons, it's equivalent to argon. 10 here plus 8, 18, and this is also octet. This is also octet. Now, for transition metal ion, a positive ion forms from an atom. Electrons are always lost first from the subshell having the largest value of n. Thus, in forming ions, transition metals lose the valence shell s electrons first, then as many d electrons as required to reach the charge of the ion. Now, for instance, in forming Fe plus 2 from Fe, which has the electron configuration this argon 3d6 4s2, now the 2 4s electrons are lost first, leading to this configuration, argon 3d6. So this gives me Fe plus 2. Now removal of an additional electron gives plus 3, iron plus 3, whose electron configuration is, you see here, the 6 becomes 5. So it's argon 3d5. Example, which element forms a plus 3 ion that has the electron configuration argon 4d6? طبعا you look in the طبعا argon 36 plus here 642, and it lost the 3 electrons, so the atomic number, the original one, 45. You look in the periodic table, you find this element called rhodium. Rhodium has this electron configuration, argon 4d8 5s1. So it loses the electron that is found in 5s, and then 2 electrons from here to form Rh plus 3. And this is its electron configuration. Now, sizes of atoms and ions. By the way, this is a section from chapter 7, 7.3. Now, the bonding atomic radius is defined as 1/2 of the distance between covalently bonded nuclei. Now, in this section, we talk about the sizes of atoms and ions. And here, when you have an isolated atom, it has the so-called non-bonding atomic radius. But when the two atoms, they tend to approach each other to form covalent bond, then this is called bonding atomic radius. This is smaller than this. So notice that the bonding atomic radius is shorter. This is shorter than this, than non-bonding atomic radius. Now, bonding atomic radius refers to the size of an atom. So the bonding atomic radius, which equals 1/2 the distance here, is refers to the size of an atom. And it's useful, for example, in predicting the carbon-chlorine bond in CCl4. For carbon, this value is 0.77 angstrom, and for Cl it is 0.9 angstrom. So bond length, the predicted one, or the calculated one, is around 1.76 angstrom, and this is very close to the measured value of 1.77. Now, this figure shows us trends in atomic radii. Now, bonding atomic radii for the first 54 elements of the periodic table we will notice the following. Bonding atomic radius tends to decrease from left to right across a row. We call this a row. So, for example, here sodium 1.54, magnesium 1.3, aluminum 1.18, and so you see size decreases as we go from left to right across a row. Why? Because due to increasing Z effective. The effective nuclear charge, when it increases, then the attraction to the nucleus is greater and the size decreases. Now, on the other hand, it increases from top to bottom. Here, مثلا lithium 1.34, sodium 1.54, potassium 1.9, rubidium, etc. Why is this? Because due to increasing value of N. Remember, as we go down, N value increases 1, 2, 3 up to 7, as we explained in chapter 2. So you should know this trend. Now, what about sizes of ions? Now, ionic size depends upon the nuclear charge, the number of electrons, the orbitals in which electrons reside. Ions increase in size as you go down a column. This is due to increasing value of N. As we said, as you go down here, لاحظوا كيف the size of the atom and the size of the ion increases. And why? Because this is due to increasing value of N. The same here for group 6A. You see the size increases for the atom and for the ion. Now, cations and anion size. Now, cations are usually smaller than their parent atoms because the outermost electron is removed and repulsions between electrons are reduced. So, for example, if we look here at lithium atom, the size is 1.34. When it loses electrons, it decreases to 0.90. And so, then, we say, cations are smaller than their parent atoms. Cations are smaller than their parent atoms. On the other hand, anions are larger than their parent atoms because electrons are added and the repulsions between electrons are increased. So, for example, here, fluorine atom, size 0.71, whereas when we add electron to it, the size increases. So, anions, all these here, are larger than their parent atoms, as you can see here. So, this is a general rule. You should always know it. Now, sizes of ions. We have an isoelectronic series is a group of ions all containing the same number of electrons. For example, each ion in the isoelectronic series above here has 10 electrons. For example, oxygen 8, it gained 2, it becomes 10. Fluorine 9 gains 1, becomes 10. Sodium 11 loses 1, becomes 10. Mg plus 2, 12 loses 2, becomes Mg. Mg loses 2 electrons to become Mg plus 2, 10. Aluminum 13, the atomic number, it loses 3 electrons to become Al plus 3, 10. So all of these are isoelectronic. Now, how do we arrange them in order of size? Now, in any isoelectronic series, we can list the numbers in order of increasing atomic number, as we did here. We arrange them in order of increasing atomic number, 8, 8, 9, 11, 12, 13. Therefore, nuclear charge increases as we move through the series. Because the number of electrons remains constant, ionic radius decreases with increasing nuclear charge as the electrons are more strongly attracted to the nucleus. Decreasing ionic radius is seen in the above isoelectronic series. لاحظوا here 1.26, 1.19, 1.16, 0.86, 0.68. So you notice that because all of them are isoelectronic and all contain 10 electrons, so you arrange them in order of increasing atomic number, the usual one, and then this is at the same time decreasing ionic radius is seen as we go from left to right, as you can see in this example. Finally, you can look at this sample exercise. Ionic radii in isoelectronic series. Arrange the following ions: S-2, calcium plus 2, Cl minus, K plus in order of decreasing size. First of all, you should prove إنه this is an isoelectronic series. فمثلا sulfur 16 plus 2 electrons 18, calcium 20 minus 2 electrons 18, Cl 17 plus electron 18, potassium 19 loses electron becomes 18. So this is an isoelectronic series with all the ions having 18 electrons. In such a series, you arrange them in the order of increasing atomic number, and then this will be also decreasing size. So مثلا sulfur 16, 17, 19, 20. So the atomic numbers of the ions are, thus the ions decrease in the size in the order as you can see here. So S-2 is larger than Cl minus, larger than K plus, and larger than Ca plus 2. Okay, this is end of part 1 in chapter 8 plus section 7.3 in chapter 7. Thank you.